So in this video, we want to find particular solutions to non-homogeneous recurrence relations. So here is a non-homogeneous recurrence relation in a general form. It is un equals p un minus 1 plus q un minus 2, and then we add on some function f of n. Okay, and to find the solution to this non-homogeneous one, what we need to do is first find the solutions to the analogous homogeneous. Start again. So in this video, we want to find particular solutions to non-homogeneous recurrence relations. So a general non-homogeneous recurrence relation is un equals p un minus 1 plus q un minus 2 plus some function f of n. And to solve this, firstly what we need to do is find the general solution to the analogous homogeneous relation. Well, the analogous homogeneous relation is essentially just this without the f of n. So it's hn equals p hn minus 1 plus q hn minus 2. And we can solve that using methods we've already done, and I'm not going to do those here in this video. I will make another one that will show us how we might solve something like that. But what we also need to do is we also need to find a particular solution to the non-homogeneous relationships, and I'm going to call this relationship here star. So we're going to call this relationship here star, and we need to find a particular solution to that, and that particular solution we're going to call Pn. And then, so we have the particular solution to star, which is Pn. And then the general solution to the non-homogeneous relation is the sum of the solution to the homogeneous equation and Pn. So the general solution un is equal to hn plus Pn. And what we want to talk about in this video is how we find this Pn. And there are some general rules we can apply. And these rules don't always work, but in this video I'm going to show you examples where they do work, and in another video we'll talk about times where they don't work. So if we consider different possibilities for the function f of n, I'll draw a little table here. So we've got the function f of n. What Pn do we consider? Well, firstly, if f of n is some constant multiplied by some number r to the power of n, then the particular solution to consider is of the form a r to the n, where there's the same r as in f of n, and we need to find that unknown constant a. If f of n is some constant, say k0, then Pn is also some constant a, and we need to find n. If f of n is linear, so it's kn plus k0, then again we're going to consider a p of n that is also linear, so it's going to be of the form a n plus b. And we need to then find the values of a and b. Similarly, if f of n is quadratic, so k2n squared plus k1n plus k0, then we have a particular solution of an squared plus bn plus c, and so on for polynomials. What we can also do is we can combine these. So let's say we had some kind of f of n that was kr to the n plus some constant k, let's call this one k1 and this one k2. Well, we combine our two results up here. So our general particular solution here would be ar to the n plus a constant, because k2 is a constant, b. Okay, and these are the general things we can do, and it works in most situations. So let's take some examples. Let's take the recurrence relation un equals 6 un minus 1 minus 5un minus 2 plus f of n. And we're going to consider different functions f of n. Firstly, I'm going to tell you that the solution to this, the homogeneous version, so we're ignoring the fn, the homogeneous version has a solution h of n equals to sum a times by 5 to the n plus b. Okay, so if our function here, f of n, was 2 to the n, so fn was 2 to the n, then the particular solution we consider would be a 2 to the n. And similarly, if f of n were, say, 7 to the n, then we'd consider p of n to be a 7 to the n. And if we consider something like f of n equals 2 to the n plus 3 to the n, then we'd consider here, well, we've got two different things here, so we'd have a particular solution of a 2 to the n plus a different constant b 3 to the n. Okay, and I think we'll go back and do one of those in a second, but let's consider some other options. So let's try a different recurrence relation. Let's try the recurrence relation un equals 9 un minus 1 minus 14 un minus 2 plus f of n. And I'm going to tell you that the homogeneous relation here, h of n, has solution a times 2 to the n plus b times 7 to the n. And let's again consider some possible functions f of n. So if f of n is equal to 2, then we consider a particular solution, p of n, which is just a constant. If f of n is equal to, say, minus 3n squared, well, that is quadratic, so we need to consider pn equals an squared plus bn plus c. And if we had something like f of n equals minus 1 to the n, we consider a particular solution pn of a minus 1 to the n. And finally, for this one, if we had f of n is equal to 3 to the n minus 3n, well, that is a combination of a linear expression and an exponential expression, so we'd have to consider pn equals a lots of 3 to the n plus a linear of terms, so bn plus c. Okay, finally, one more example. If we take the recurrence relation un equals minus 10 u to the n minus 1 minus 25 u to the n minus 2 plus f of n. Well, the solution to the homogeneous equation to this is h of n equals a minus 5 to the n plus b n minus 5 to the n, and you just have to believe me there. Then what do we need to consider? Well, let's consider when f of n equals 5 to the n. Well, a particular solution we can use here is p of n equals a 5 to the n.